That leads us into a model of gas behavior, kinetic molecular theory of gases. So we've been talking about what happens, the laws, but we haven't talked about why. The what always comes before the why, because you can't explain something if you don't see a pattern. If you can't say this is what happens, you can't explain why it happens. So what always comes before why. So kinetic molecular theory, the word kinetic has to do with motion, and molecular has to do with molecules. So this is a theory of gases based on the movement of the particles. And there's a few postulates, and we'll go over them one at a time. So the first idea is that gases consist of tiny particles. These can be atoms or molecules. This is not something that you can really figure out just with your five senses, because gas particles are so small we can't see them. And so it took scientists a long time to figure out that gases were actually particles. And this is definitely accepted to be true. The particles are so small compared to the distances between them that the size, the volume of the individual particles is negligible. Essentially, we can say, based on the size of the gas itself, the space it occupies, the size of the particles is so small we can essentially neglect it. We can say they're zero. So this reminds me of some family vacations. We used to drive to Minnesota to visit my parents, and we would go through Wyoming sometimes. Have you guys ever been to Wyoming? Wyoming's a cool place. The population of the entire state is about the same as the population of Fresno. Without Clovis. Just Fresno. So, 450,000 in the whole state. And it's not a little tiny state like Delaware or something. It's not as big as California, but it's a good-sized state, 400,000 people. So you notice this when you're driving through Wyoming at night, because you can drive for miles and miles and miles and not see a light. Now, we have country around Reedley, and Reedley's a small town, but you drive at night and you see farm lights and house lights, right? You see lights. You can drive for miles in Wyoming and not see one farm light. It's really kind of mind-boggling. Most of the state is just like empty. There's a lot of cows. I think the cows probably outnumber the people. But it's very empty. It's beautiful, but very empty. And that reminds me of gases. Okay, so think of the 400,000 people and the volume of that state. Does the size of the individual people in that state really matter? Whether they're all, skinny little 100-pound people or, big hefty 300-pound people? Does it really matter to how much space they have? No. Now think about 10 people in an elevator. Now, does it matter whether those 10 people in an elevator all weigh 100 pounds or 300 pounds? It does, because the volume that they're in is small relative to the volume of the people, right? So that's more like a solid or a liquid, where the particles are very close together, and there the size of the particles matters. But in a gas, they're so spread out that the size of the particles doesn't matter at all. Okay, so that's what this postulate is saying. The volume of the individual gas particles doesn't matter. So whether the gas is really big molecules, little tiny molecules, doesn't matter for the behavior of the gas. The particles are in constant random motion, colliding with the walls of the container, and those collisions cause the pressure that's exerted by gases. So I'm going to draw you a picture. It's like drawing picture day, right? Most of you are probably too young to remember it was just so innovative and awesome. Pong. Have you at least heard of Pong, the video game Pong? It was like one of the first video games ever. It was on the Atari system, and we used to think it was so fun. So for those of you who don't remember. Yeah, exactly. And so the way Pong worked is you had this little they called it a paddle. It was a line, okay? And you could move the line back and forth, right and left. I mean, it's just very high tech. And then there was this blip. And this blip just went in a straight line at a constant speed until it bumped into something. And so it would go here, and then it would bounce off according to the laws of physics, and it would bounce off here, and it would come down here. And you better move your paddle over there and get your paddle under it, otherwise it would go right down here and go, you're done. And about the only thing you could mess with is if it hit the paddle when it was moving, you could like get it to go off in funny directions. But if you put your paddle in just the right place, like she said, you could sometimes, that's not a good place, but you could sometimes get it to just bounce continuously. I think of gas particles like that. They're just like little blips, and they just move in a straight line until they run into something. They run into each other occasionally, and they run into the walls. Like, we could think of this room as a gas container. So we've got walls here, and there are gas particles hitting the whiteboard. There are gas particles hitting you in the face. There's gas particles hitting the ceiling and the floor of my computer screen. And so it's like this Pong game with gazillions, little tiny Pongs, okay? And they're just bouncing around like that. And they just go at a constant speed until they run into something, and then they bounce off and they go somewhere else. And that's what gas particles do. So they're very tiny, and so when a little tiny gas particle hits the whiteboard, it doesn't make much of an effect, right? But there is some effect. There is a pressure exerted by that particle when it hits the wall. And these little teeny tiny pressures add up. Because, my son Andrew is 5. So when he punches you, he's getting stronger. It was easier when he was like 2. We'll go back to 2-year-old Andrew. So 2-year-old Andrew, he'd like to beat up on his teenage brothers. And so, he'd come up and he'd be hitting you with his little tiny fists. And does that hurt? Not really. But if he just keeps doing it, okay, it's like being pecked to death by a duck, right? Little tiny pecks, but after a while it adds up. It's like a fly, Fly comes and lands on your nose, and you shoo it away. The first time, no big deal. After it's landed on your head like 25 times in 3 minutes, you're just ready to kill that thing, blow up the room to get the fly to go away, right? Little things add up. And so these little collisions from these gas particles are what account for the pressure of a gas. The other thing that we assume is that the particles in a gas do not attract each other or repel each other. And I think of this, in terms of Wyoming and those people too. If you took those 400,000 people in Wyoming and you spread them all out, would they have much interaction with each other? No, because they're probably so far away from each other, they can't hear each other yell, they maybe can't even see each other. How can you interact with someone when you're that far away? And these particles, these gas particles, are very far away from each other. And when they do touch, they are both moving and they don't have enough time to interact, and they just bounce off each other and go on their way. So that's our assumption, is there's no interactions between the particles. Now, the energy of those gas particles is related to the temperature of the gases. Here is the equation for the kinetic energy of a moving object. And I'm not going to test you on this, but I'm just going to show it to you. The kinetic energy of an object is 1/2 times the mass times the velocity squared. So the kinetic energy of something depends on the velocity much more than it depends on the mass. You think about, say, football players running into you, right? And so you've got a guy just walking towards you and bumps into you. Is there a lot of energy in that collision? Not a lot. What if he's running at you full speed? You're going to go flying, right? Velocity matters. Well, the velocity of the particles depends on the temperature. And kinetic energy is a measure of, temperature is a measure of the kinetic energy of gases. And so we find that the kinetic energy of the gas depends on the Kelvin temperature. It's directly proportional to the Kelvin temperature. It's related to the Celsius temperature, but it's not a direct proportion. So temperature, Kelvin temperature again, directly proportional to the average kinetic energy. And we say average here because not all of those particles are moving at the same speed. Some are going faster, some are going slower. But when you heat them up, you increase the average kinetic energy, you increase the average speed. So gas pressure increases when the temperature increases because the particles speed up. So in our gas laws, we looked at the relationship between pressure and temperature. If you heat a gas, what happens to the pressure? Does it go up or down? It goes up. Well, kinetic molecular theory helps us to understand that. When you increase the temperature of a gas, you make the particles move faster. What's that going to do to the number of times they run into the walls? If they're moving faster, they're going to run into the walls more often, right? And each time they hit the wall adds to the pressure. They're also going to be hitting faster. They're going to be hitting harder. And so each collision is more pressure. So when you increase the temperature of a gas, the pressure goes up. The volume of a gas increases with temperature also because the particles speed up. If you allow the pressure to remain the same, but you increase the temperature, the gas will expand because the particles are moving faster. So these are some kind of useful questions. So we're talking about two balloons. There they are. Helium balloon and a hydrogen balloon. They have the same volume. Can't read today. The same volume. So we look at them and yeah, those look like the same volume. And so there's going to be some statements coming, and we're going to finish those statements with the word same or the words point to different and say the same. That's fabulous. I'll just read this. Complete each of the following statements with different or the same. Be prepared to justify your answer. So, given that we have these two balloons with the same volume, the pressure of the gas in those two balloons, is that going to be the same or different? It's going to be the same. And so then we need to idea of why, because just random guessing isn't the greatest. Why are the pressures the same? They're at the same temperature, they're right next to each other, the same volume. Does it matter that one's helium and one's hydrogen? Does it matter if it's 400,000 newborn babies or 400,000 7-foot tall basketball players in Wyoming? Does the size of the people matter? No, the size of the particles doesn't matter. So it doesn't matter that these are two different gases. Same volume, the pressures are going to be the same. The temperatures of the gas in those two balloons. It's going to be the same also. How about the number of moles of gas in these two balloons? They're at the same volume. Didn't mean to do that. Same volume, same temperature, same pressure. How about the number of moles? Number of moles tells us how many particles, right? The number of particles is also going to be the same. It doesn't matter what the particles are. The number of particles is going to be the same. Because if we do PV equals nRT, the ideal gas law, for each of those balloons separately. The volumes are the same, the pressures are the same, the temperatures are the same, the number of moles have to be the same. Because this equation is true for both of those balloons, regardless of what gas there is in there. It could be argon or carbon dioxide or anything. What about the densities of the gases? You remember the equation for density? Density equals mass over volume. Well, we already said the volumes were the same. Are the masses of these the same? Same number of particles. How much does a mole of helium weigh? 4 grams. How much does a mole of hydrogen weigh? H2. 2 grams. So the moles weigh different amounts. We have the same number of particles, but they don't weigh the same. So the masses will be different. Where'd my arrow go? If the masses are different, but the volumes are the same, the densities are different. Think about party balloons. So you've got 2 identical balloons, and one of them you blow up with your breath, right? And you tie it off. And the other one you blow up using a helium tank, and you make them exactly the same size. Are they going to act differently? The helium one's going to float, right? The one that you blew up with your mouth is not going to float. Why? The density of the gas is different. You probably have the same number of particles of gas, but the particles weigh more. The particles weighing more does not affect the pressure, the volume, the number of moles, the temperature, but it does affect the density. Helium balloons float because helium is less dense than air, just like oil floats on water, like wood floats on water because it's less dense. Less dense gases will float in greater density gases. So, yeah, you can watch the cartoons and they violate the law of physics all the time with the whole balloon thing. Remember Winnie the Pooh? Christopher Robin blew the balloon up for him, and then he floats up to the tree to get the honey. This doesn't work. And Mythbusters has also proved that it would take way more than one balloon to lift anything off the ground. They did a whole show on that. That was pretty interesting. I don't want to do that one. Oh, we can talk about this one. So here we have a gas. We got nitrogen in it, and it's a piston, so the lid slides, and the pressure's going to stay the same. It says initially the gas is at 45 degrees Celsius, and the volume is 6 liters, and now we're going to cool it. So we're going to make it colder. So what's going to happen? When we take that gas, the pressure's the same, the number of moles of gas is the same, but we're reducing the temperature. Is the pressure going to increase? No. Is the volume going to increase? Well, let's think kinetic molecular theory of gases. What happens to those particles when we cool them down? They slow down. Okay, so that means that they're going to collide with the walls less frequently and with less force. So what's that going to do to the pressure? That would make the pressure want to go down. But the question said that the pressure was staying the same. So if the pressure stays the same, and these gas particles are moving slower, what's going to happen to the volume? It's going to get smaller, right? Because I really don't like how this book explains this. They kind of go off on these things. So pressure is a force divided by an area. We talked about that, right? It was a while ago. It was before spring break. Maybe you don't remember. Pressure is a force divided by a unit area. When someone stands on your stomach on one foot, that hurts more than when they lay flat on your stomach, right? Same amount of force. It's their entire body weight. But because it's spread over a larger area, if they're laying on top of you, it doesn't hurt as much because the pressure is less. If they're standing on one foot on your stomach, that's going to hurt more. There's more pressure, right? So that's what happens with gases too. So the force of the particles is going down because the temperature is decreasing. The pressure is trying to stay the same. So if the top of this fraction decreases and we need it to stay equal to the same number, then the area must also go down. So in this container, what's the area? Well, it's the area of the inside of the container. How can we make the area smaller? If we bring this piston down, make the volume smaller, then the area will be smaller, right? Does that make sense? Without getting into geometry and equations? So to keep the pressure the same, when the force goes down because the temperature went down, the area must go down. The area that these gas particles are hitting over depends on the volume of the container. So when the temperature goes down, the volume will go down. So the volume is not going to increase. The pressure decreases. If it wasn't in a specially rigged up container that maintained the same pressure, we might expect that the pressure would go down. But that container maintains a 6 atmosphere pressure. How about D? The volume of the gas decreases. Yeah, that's the one we're looking for. The pressure can't change, only the volume's allowed to change. So the volume will go down. And I don't know if you've had this experience, we take the kids to a party in the winter and they bring home helium balloons and they fall asleep in the car on the way home, and then you leave the balloons in the car because you forget to go out for them. Come out the next morning, it's like 32 degrees outside. And those balloons are smaller than they were, right? They're smaller, and now they're kind of sitting on the floor. You're like, oh man, I left the balloons out here. You bring them into the house, they warm up, they get a little bigger, and a lot of times they'll start to float again because their mass doesn't change, but when they expand because they warm up, now their density changes and they'll start to float again. This is something you can try at home. Take a balloon and blow it up, tie it off. Don't blow it up too big. Put it in a bucket of ice water. And you should be able to see that the volume gets smaller, the balloon gets smaller. Then take that balloon and put it in some boiling or really hot water and see what happens to the volume of the balloon. As the air in the balloon increases in temperature as it warms up, the balloon gets bigger. And you can do that over and over and over until the balloon breaks. It's one of the kind of fun things about gases is, we've all had some experience with balloons. We know how gases act because of our experiences with balloons.